Hello, Professor and TA. My name is Mohammad Armuganuddin, and as part of our CS147 project, I will be developing a parallel version of a hashing algorithm used for cryptocurrencies. I went through a lot of hashing algorithms, and I noticed that Bitcoin is the most popular cryptocurrency. So I thought I would parallelize the SHA-256 algorithm, which is used in Bitcoin. Now, the SHA-256 algorithm is a very unique algorithm. So what happens is, like, irrespective of our input size, it is always guaranteed that we'll get a length of the hash of size 256. This is very unique because although the SHA-256 hashing function is deterministic, as in if I input two same strings, I'll get the same hash out of it irrespective of the length of the string. If I give a length of a string of size 100 or 2, I am guaranteed to get a hash of length size 256. This is why it is used in cryptocurrencies, and it is also used in a lot of decentralized stuff, such as for digital signatures, such as creating hashes of the transaction details as well as the headers. So this function is used a lot in the proof of work mining algorithms. So firstly, let's jump right into our code. As we can see, I have a number of files here. Now, initially, one of my biggest hurdles which I faced was to generate the testing data. In fact, our professor Daniel Wong also had highlighted to me that how are you going to generate the testing data for this? So I brainstormed a bit, and I know for a fact that the passwords stored in websites are usually hashed, and there might be various hashing algorithms for it, but it could be possible that the website is using the SHA-256 algorithm for hashing the passwords. So what I came up with is, like, I extended my project and I converted it into more of a password brute forcing application. So basically what it does is, let's just say I have a password, and I also have the SHA-256 hash of the password, which is basically what will be stored in the website. So what I do is I brute force all the combinations of the passwords which I can generate of a specific length, and then I compare the two hashes. In here, I am utilizing multiple aspects of parallel GPUs, because what I am doing is I am parallelly finding all these combinations as well as finding the hashes of all this in parallel and comparing the answers. So I have a maximum length of the password set as 10, but I can input any password and I'll be getting that. I've set it as 10 because it's gonna take a lot of time to go beyond 10. So let's just see our code first. This is my parallel SHA-256.cu file, which is basically my entire implementation. Here we have the hash length, which is set as 32. The maximum password length, which I mentioned, is set at 10, and we have the thread per blocks and the number of blocks set. First of all, we have the password generator. Here I'm generating the password. Since I am doing this in parallel, I have assigned this as a GPU function. Then we have the memcmp function, which is nothing but basically comparing the two arrays. So basically, once I have the two hash functions, that is of the original password as well as the password that I'm currently trying. Like, let's just say my original password is ball, and I'm currently trying a 4-letter combination, which is maybe ABCD. So this function will basically compare the two hashes and see if they are equal or not. This is my password cracker function. And here I am implementing the parallel version of it. So as you can see, first of all, we are finding the SHA hash. I'm also finding the hash of the original password here. But obviously, in, like, if we are seeing this in an ideal scenario, I must already have the SHA 256 hash of the password we are trying to crack. But just for testing purposes, I have developed this aspect of my project so that I can test with various passwords and I don't have to just input the hash, which is quite cumbersome. So basically, this allows me to just input a password and it's converted to a hash. And then I'm just finding to crack that hash. As you can see, I'm just comparing here. Like I mentioned, using the device memcmp function, which basically compares the two hashes. And then we have the atomic add function, which studied as part of our project. What it basically does is, when I'm trying to compare the speed of the two functions, it is very crucial that I know how many hashes I have already processed. Now, here, the atomic add, what it does is it basically ensures that we are not ending up in a race condition. Since there are multiple threads working on to calculate the various passwords and trying to crack it, it's very difficult to keep a track of keep a single variable and just keep a track of how many passwords we have attempted. Using atomic add, we will ensure that we are incrementing the variable properly and no two threads end up uh, updating it at the same time, which can cause race conditions. Here, get time in seconds is just a simple function which I am using to keep a track of the time. Host alphabet is usually just a string to where I am using to calculate all the various possibilities which I can have for a password of a given length. Then, if our C is greater than one, this is just to get the input. And here I'm just declaring the device variables, copying them. And this is the main function where I'm doing, where I'm generating all the possible combinations and to using the various threads to find whether the given hash is equal to the original password or not. On top of that, I have a sequential version of the file, which is pretty simple. It just computes all possible variations and compares it with the SHA-256 hash of the password I have. As well as I have a few files linked. This CA SHA256.c and H are the regular SHA256 algorithm, and the CUH file is basically the parallel version of the algorithm, where what I am doing is here all the functions are device functions so that I can run them on parallel. And on top of that, a very important thing is I'm using loop unrolling here so that the loops are processed in parallel. Now I quickly want to jump to the implementation, and I can just do git clone to get my repository here. And once I have the repository, I can change my directory to that. And let's just say I am running a file. I am running the parallel version of it first, and I will just put my name, ARMUG. So I am putting a 5-letter password, and if I'm running it, I'm getting the password cracked in half a second. Now, if I compare this to the sequential version, instead of trying the 5-letter, let's try with the first 4 letters of my name. And as you can see, it's already been more than half a second. And so it's taking 5.5 seconds to crack 4 letters of my name. But if I make it to 5 letters, it's gonna take quite some time because as per my experimental data, which I have performed here, it's taking roughly 118 seconds as compared to the parallel version, which takes only half a second. And I've also made a graph for this, which basically compares the execution time of the two, the parallel and the sequential version. And at the same time, I tried beyond 5. I personally didn't try for the sequential version, but considering that the number of combinations is roughly 50 times, and I calculated it takes roughly 12 minutes to find a combination of 5 letters. It's gonna take over 2 hours to get a combination of 6 letters. But at the same time, when it comes to the parallel execution, I'm able to get an answer in like 40 seconds or 45 seconds from some of the tests which I have done. As you can see, I have reached 4 letters in 15 seconds, all combinations of 4 letters, but I have still not found the 5-letter passwords I'm trying to find, which is ARMUG. It's going to take roughly 118 seconds to do this. And this basically shows how much faster the parallel implementation is. We are using the parallel implementation in multiple stages of our program, as I have highlighted in the implementation. So we are also calculating all the combinations in parallel. We are also doing the hashing in parallel. And this project is going to be it's very it was very difficult to come up with the testing data. So this is what I came up with to give a better understanding of how fast the parallel version of the hashing algorithm can be. Uh, that's all from my end. Thank you, Professor, for allowing me a chance to do this wonderful project. It was a great learning experience for me, and I'm looking forward to studying with you again in the future. Thank you.